So in this talk, I will talk on compactness of state space in classical Banach space. And this is a joint work with Saurabh Dwivedi from Shivnadar Institute of Eminence, Delhi NCR. This is basically outline of my talk. First, I will introduce some notations in Banach space. Then I'll discuss some preliminary things on state spaces and topologies on the dual space of a Banach space. With respect to that topology, we'll discuss the state space, whether it is whether the state space is compact with respect to that topology or not. Then we study this compactness of state space in space of sequences of vector, and then in space of vector valued functions. So let me introduce few notations. For the talk, I will use X for Banach space over scalar field K. Here K can be real or complex, and unit ball of X and unit sphere of X will be denoted by this x1 and s of x respectively. X star stands for dual space of X, and C naught is space of all null sequence with sup norm, and L1 is space of all sequence such that summation of absolute value of that sequence is finite with this L1 norm, and C omega, where omega is a compact Hausdorff of space, is set of all continuous function with this supremum norm, and L1 mu is space of all measurable functions such that this integration is finite with this norm. So let us start with the definition of state space in unital system algebra. So if we take A to be a sister algebra with unit I, then state space of A basically this set of all elements in the dual unit sphere such that if that unit sphere such that that function at I is equal to 1. I mean that if that function is rho, then rho of I equal to 1. Now, motivated by this definition, Rao has introduced this set as a state space in Banach space. And in the following article, he has studied the compactness of the state space in Banach space. So, let me define that state space in Banach space. Let X be a Banach space and small x be unit vector of that Banach space X. Then state space of X at the point X is defined by this set of all norm 1 functional such that X star of X equal to 1. So it is also known as set of all support function of dual unit ball at the point X. So now people can ask that whether this set is non-empty or not. Yes, it is non-empty by Hahn-Banach extension theory, and this set also convex. In fact, it is a face of Bx star. That means if any line segment in Bx star intersect with Sx, then the entire line segment should be in this Sx. And this state space is well connected with the differentiation of that Banach space in this following way. If the state space is singleton, the state space is singleton if and only the norm of X is Gato differentiable at X. So we mainly discuss the compactness of state space with respect to the following three canonical topologies on X star. So the norm topology, the topology on X star induced from the dual space, induced from the norm in the dual space. Weak topology, the smallest topology on X star such that all element in bidual are continuous with respect to that topology, and weak star topology is the smallest topology on X star, so that all these type of functions are continuous. This is basically canonical image of canonical embedding map and defined by this way. Now, if we recall the definition of state space, so it is easy to check that it is norm, weak, and weak star closed in Bx star, where Bx star is unit ball of X star. It is also easy to check that it is weak star compact, but we don't know, in general, we don't know whether it is norm compact or weak compact. Now, the study of state space is well connected with the smoothness of a Banach space. A Banach space is said to be smooth if every state space is singleton. So, in this case, the state space is compact with respect to above all three topologies. Now, the motivation behind the study is the following. Professor Rao has derived this result. Like if the state space in unital sister algebra is weakly compact, then A is finite dimensional. So this tremendous result motivates us to study the state space in Banach space. So basically, the last one was the motivation for weak compactness of state space. Now we discuss a motivation on the norm compactness of state space. So before that, I introduce this strong subdifferentiability in Banach space. The norm of a Banach space is strong subdifferentiable at a point X if this one-side limit exists uniformly. So if you remember the definition of Hesse differentiability, this is basically one-side limit of the Hesse differentiability. And one can also check that Gato differentiability plus this strongly subdifferentiable if and only Hesse differentiability. Now the motivation behind the study of norm compactness of state space is the following. So if the norm of a Banach space is SID and all state space are norm compact, then this SID passes through the quotient. And in general, if X is, of course, here we consider that the subspace Y is functional subspace. So in general, it is not true, but if we assume that all state space are norm compact, then it is true. So let us discuss some example in very classical Banach space. So first we discuss in C0. So if we choose an unit vector in C0, let us say this alpine sequence in C0, then it is smooth if and only this is of this form, where A is scalar whose modulus value is 1. So basically this sequence is A En. That means at nth position it is a L star, it is 0. And all state space in this of C0 is norm compact as well as weak compact. So if we consider if we consider a sequence in unit sphere of L1, then it is known that it is smooth if and only all coordinates are non-zero, and the state space of at that point alpha n is norm compact if and only this lambda is finite. This lambda means that of all n where alpha n is 0, where alpha n is the nth coordinate of that sequence, and we can check the similar result too for weak compact. So let us consider the study in capital L1 space. Let mu be a finite measure and f be an element in unit sphere of L1 mu. Then f is smooth if and only it is not equal to 0 almost everywhere. So this is basically generalization of that discrete case, that small L1 case. And one can also check that state space at F is norm compact if and only F is smooth point in L1. And again we have similar result for weak compact. Now if we consider an element F in C omega, and we denote gamma by the gamma, we denote gamma is the norm attainment set of F. Then one can check F is smooth if and only that gamma is singleton, and state space at F is norm compact if and only this gamma is finite, and we have similar result for weak compact. So now we discuss the study in spaces of sequences of vector. So first we consider L1x, where L1x is sequence of vectors such that summation of norm of xn is finite with this norm. This is basically vector valued. We can say it is vector valued small L1 case, scalar L1 case. So first we consider and unit vector, the sequence xn, whose every coordinate is non-zero. Then we can check that it is smooth if and only it is coordinate wise smooth. Of course, we take normalization. We normalize the coordinate element, and the state space at that sequence is norm compact if and only. So it is coordinate wise norm compact, and this diameter goes to 0. And we have the similar situation in weak compact case. So in the last result, we assumed that all coordinates are non-zero. So in general, we have this, like if xn is a sequence in unit pair of L1x, then it is smooth if and only every coordinate is non-zero, and that xn by norm of xn is smooth for all n. Now for norm compactness, we consider X to be finite dimensional space. Then the state space at the sequence Xn is norm compact if and only this lambda set is finite and diameter goes to 0 as n tends to infinity. For weak compact case, again we have similar result, but in this case we consider X to be reflexive. So this is basically generalization of C naught. The C naught x, here the C naught x is set of all sequences of vectors that norm of xn is equal to 0 with this norm. So in this case, we have derived that a sequence from unit sphere of C naught x is smooth if and only the sequence of this form, where En is this is basically element whose nth coordinate is x, this capital N, for some n belongs to this lambda, and this x capital N is smooth in X. Now the state space at this sequence is norm compact in dual of that C naught x, which is L1 x star, if and only this S of xn, state space at xn is norm compact in X star for all n belongs to this lambda. Again we have similar situation for weak compact case. So now we consider that space of all Bognor integrable function, we denote that space by this one, but in this case we consider mu to be Leibniz measure. So in this space, if we take an unit vector such that it is non-zero almost everywhere, and we also assume that x star is separable. uh, yes, we need x star is separable. Then we can check if it is smooth, if and only if this point is smooth everywhere. And the state space at F is non-compact if and only F is smooth, and we have similar result for weak compact. Now the smoothness case first shown by Dev and Khalil in the following paper. They mainly use the Karutuski real Narjeski selection theorem, but in this work we have given an alternative proof using the von Neumann selection theorem. So in the last case we assume F not equal to 0 almost everywhere. Now we consider the general case. So if we assume any unit vector from this space, and here also we consider x star is separable, then F is smooth if and only F is F is not equal to 0 almost everywhere, and it is pointwise smooth. For norm compact and weak compact, first we define this modulus function, I mean mod of this F. For F belongs to L on mu x, we define mod of F by this way. Then one can check if F belongs to L on mu x, then mod of F belongs to here, and norm of F equal to 1, then norm of mod of F equal to 1. Now let x be Banach space and mu be Lebesgue measure on this, and we assume F an unit vector in this space. Then F is smooth if implies mod of F is smooth in L on mu. And we have similar situation for norm compact and weak compact space. I mean the state space at F is norm compact and mod of F is smooth in L or mu, and state space mod of F is smooth in L. So now we consider space of all vector valued continuous function with this supremum norm, and we denote this lambda is set of all norm attainment, set of all point where this norm attained. I mean norm attained of this function. Then if this set is finite and it is pointwise weakly compact for every point in this set, then the state space is weakly compact. And we have similar situation. Sorry, here first one should be state space is norm compact, and second this one should be state space is weak compact. And the converse is true if the x satisfies this inclusion. Now example of a Banach space which satisfies this example and this inclusion is C omega. In fact, if we take any closed subspace of C omega which contain the constant function 1, then it satisfies this inclusion. So, throughout the talk, only I discussed that P equal to 1 case, but I didn't consider for P greater than 1. In fact, for capital L1 case, I consider only on this 0 on only on this measure space. I mean the measure space is Lebesgue sigma algebra with Lebesgue measure on 0 1. So now the general case are open. If we consider P strictly greater than 1, then we don't know the characterization of state space in LPX. Here what I said that if mu be any finite measure, non-Lebesgue measure, then what can we say about the state space of that L on mu x? And again we have similar question when P greater than 1. So this talk is based on this first paper, and this so basically alternate is a smooth fast smoothness result first proved in this paper, and the motivation of this talk of this work was by this paper. Thank you for everyone.